Hello friends, in this video we are going to discuss about Raman spectroscopy, and the most interesting part is we are also going to discuss about data interpretation. So this video is very useful for a researcher who want to understand about Raman spectroscopy and also analyze its data. This is the list of content. We are starting with the origin of Raman effect, then the science behind, then as a characterization apparatus, then we will move forward towards what are Raman modes, Raman versus infrared spectroscopy, Raman active and inactive states, and finally the data characterization. So this video will overall give you all the necessary information required for understanding Raman spectroscopy and analyzing its data. This video is sponsored by nobody, because my views don't shoot like they do for popular science videos. This is highly research oriented and concentrated experience knowledge, not appealing for general public. Instead, I would say that this video is sponsored by you, because you are the main supporter of my content. So if you find this video useful, please don't forget to contribute whatever you feel is okay for this content. So let's move forward. Raman spectroscopy was discovered by Chandrasekhar Venkat Raman, an Indian scientist. He saw the blue color of Mediterranean Sea and was curious about how this color is blue. So that curiosity led to the discovery of Raman effect, which is one of the prominent characterization in material science nowadays. So let's move forward and discuss about the origin of Raman effect. Basically, Raman spectroscopy observes the change in the energy between the incident and the scattered photons. You have a laser source and some sample. You illuminate that sample using that monochromatic light. It scatters light, and three kinds of radiation we observe. One is Rayleigh, one is Stokes, and one is anti-Stokes. Rayleigh is same as the incident one. So we use a filter and block that. Then we have Stokes and anti-Stokes. Then we have a wavelength selector and we get the data. The intensity of Stokes is higher than the anti-Stokes. That's why we use just the Stokes. But now the question is why this energy is different in Stokes and anti-Stokes. We need to understand this at atomic level. So for individual atoms, if we look at, there are only ground and excited electronic states. So there are no other states. But when we talk about molecules, there are also vibrational energy levels and the corresponding rotational energy levels. So now with each energy, there are also some other energy levels associated with them, which are assigned to vibrational energy and rotational energy. Now let's look at how an electron transits from lower to higher level. Near the bottom we can see the ground state vibrational energy levels, and near the top we can see the excited state energy levels. So first we are illuminating sample with a certain light. Because of this light, electrons are getting excited from the ground level to the higher levels, which we can see as a leftmost arrows. Now this is possible and a dominating effect that these electrons, without any change, they just come back to their original energy levels and emit the same kind of radiation which excited them. This is known as Rayleigh scattering, which is of no use for us basically, because this doesn't have any information about the material. But the most interesting part comes in the picture when they switch their energy levels. They don't go back to the same energy levels from where they came. And the case when they are of lower energy, so they are known as Stokes, and when they are of higher energy, they are known as anti-Stokes. Overall, because of Maxwell-Boltzmann distribution, at higher energy there are lesser particles, or in this case we can say lesser electrons. Near the ground state vibrational energy levels, at zero level there are more electrons present, so more electrons will go to the higher state. At level 1 there are comparatively less number of electrons, so less electrons will go to the higher levels. So in case of excited state, obviously there are more particles at zero level and there are less particles at level 1. This is the reason that the Stokes emission is much favored over anti-Stokes. But both Stokes and anti-Stokes carry the same information. The intensity of Stokes emission is higher, that's why we prefer Stokes radiation. Their relative intensity also changes with temperature, because according to Maxwell-Boltzmann distribution, as temperature increases, the distribution of these electrons in the energy level also changes. So according to that, the relative intensity of Stokes and anti-Stokes also varies. So that is a considerable fact. Now we have come to know about the transitions. But why there are different vibrational energy levels? This is the next level question. And to understand this, we can imagine atomic bonds like elastic springs. They also obey Hooke's law, and the atoms in a material like mass centers. Whenever we give some energy to this, these elastic chain of atoms also oscillate, and each lattice vibration in the periodic solid structure is like a standing wave and also known as a normal mode. Just like in waves and oscillation, we study about normal modes. This quantum of crystal vibrational energy is known as phonon. So the fact of the matter is, the chain of atoms absorb energy and can hold that energy in terms of that lattice vibrations. Let me tell you more about normal modes. So in case of a guitar string, every string is oscillating at its own normal mode. So we can see that there are standing waves in each case. And also we should add this point to our knowledge that a single chain of atom can vibrate with different normal modes simultaneously. So it means all these normal modes are carried by a single chain of atoms simultaneously. This is a simplest one-dimensional example, but also in case of two-dimensional network of atoms with their bonds acting like springs, we can see such vibrations, and each direction carries its own normal modes. Similarly, we can also imagine a 3D lattice vibrating in its own way. Many physicists use group theory to consider all the possibilities of vibration in a structure of atoms. So their Raman activity, inactivity is another thing, but all the vibrations possible could be suggested by group theory, and physicists do that. Now if we talk about the next thing, according to quantum mechanics, the energy corresponding to each normal mode is like this: n plus half h cut omega. So here n is an integer, omega is k by m square root. So k is the spring constant, which is basically correlated to the nature of the bond. If bond is very strong, it means the spring is very much stiff. If bond is very light, it means it's a light spring that can be easily stretched. And also the mass of the participating atoms is involved. If these are heavier atoms or lighter atoms, this affects the energy. When there is an isotropic medium, the vibrations are same in all directions, but in case of anisotropic media, these vibrations are not the same. So overall, we made a platter of information regarding the science behind Raman spectroscopy. There is a lot more information to learn about Raman spectroscopy, so this is summary part 1. So you have just learned with electronic transitional energy levels, there are vibrational energy levels. Electrons also switch their vibrational energy levels, and when they switch it, they don't emit the same radiation they were illuminated with. So that variation tells us about the properties of the material. The energy of each normal mode depends upon the spring constant and the mass of the atoms involved. Spring constant is directly related to the nature of the bonds and the interatomic distance, and the mass is directly related to the mass of the atoms. Raman spectroscopy targets the change in energy from the incident radiation, and observing that energy is Raman spectroscopy. Now let's talk about Raman as a characterization. It is very easy characterization. It doesn't take much time, no special sample preparation, and humidity also doesn't affect it much. So that's why it's very useful, and you can perform it very easily. Nowadays, many handheld devices are also present in the market, so that you can just carry them with you and analyze Raman spectra anywhere you want. In its apparatus, as we have discussed earlier, we have Stokes and anti-Stokes light, but when we observe a data, we take only Stokes line for our analysis. Now let me also tell you that what is in a wavelength selector. Many different kinds of wavelength selectors can be used, but one of the common design is like this. There is an optical device known as reflection grating. So when an incident ray strikes with it and getting reflected, different wavelengths are reflected in different directions, and we place a detector at that particular point. So as we rotate this reflection grating using this motor, we observe intensities of different wavelengths, and finally we are ready with the data. So this was about its apparatus. Now let's discuss about different Raman modes. So we are choosing a diatomic chain of atoms, and there are two kinds of phonon modes, acoustics and optical. In case of acoustic phonons, A1 and A2 oscillate in phase, and for optical, out of phase, as we can see in these diagrams. So there are two categories, longitudinal and transverse. Along with that, we can see acoustics and optical. In case of longitudinal, in the same line of motions, atoms are moving, so that is known as LA, longitudinal acoustic phonon mode. There are two kinds of atoms, black and red, A1 and A2. They are moving in sync, and as we see in case of optical phonon, red are moving towards a center to make it a compression, while the blacks are moving on the other way. Similarly, for the transverse, a diatomic chain of atoms can show different normal modes. Besides this TALATOMO modes, there are additional information as prefix suffix attached with each mode. So if in prefix some letters A, B, E, T or F are written, so they have some specific meanings for these modes, that these are one dimensional, two dimensional, three dimensional, singly degenerate, doubly degenerate or triply degenerate, like this. So these terms as prefix give more information about these modes. In subscript, if GU1 or 2 they are written, so they tell about whether these modes are symmetric or antisymmetric to inversion center of molecule. 1 and 2 means if same transverse optical mode is available at two places in the range, so we call it TO1 and TO2. And in superscript, if we see these signs, so symmetric and antisymmetric to a mirror plane. First we understood about the normal modes, and now we have understood about their nomenclature. And as a very short summary, we know that we are preferring Stokes lines for data analysis because of higher intensity. Raman is a simple and fast technique and unaffected by the humidity interference. Also, the variety of lattice vibrations are identified as different Raman modes. Their nomenclature is also present. Raman modes can also be predicted by group theory and some quantum mechanical techniques through which each mode and its respective intensity can be predicted. As we have discussed that the Raman spectroscopy is basically the difference of vibrational energy levels while excitation and de-excitation, and IR spectroscopy is similar because this also deals with the vibrational energy levels. But what is the overall difference between them? To understand this, let's first discuss about what is IR spectroscopy. So you have a material, you incident some light on it, and in a particular wavelength range, that material absorbs that light, and you come to know that this is the particular energy of which vibrational energy levels are available in that material, and you get to know about those vibrational energy levels. A molecule is IR active if vibrational transition result in change in molecular dipole moment. In Raman spectroscopy, we fall some light on the material, it scatters some light, and out of scattered light we are observing only Stokes light. With respect to the incident, what is the change? We are observing that change only. That's why it is also known as Raman shift. As you can see in the figure on the right hand side, a molecule is Raman active if the vibrational transition results in change in molecular polarizability. Because both of these characterizations discuss about the vibrational energy levels. That is why their data are generally in agreement with each other. Let's add more information to this. So when we are talking about Raman activity, in a molecule the atoms are at a mean distance from each other. So when some energy is incident on a material, this distance varies. If the polarizability varies asymmetrically, in that case the material is Raman active, otherwise the material is Raman inactive. So in each material certain modes are Raman active, which show the variation in energy, and certain modes they don't show the variation in energies and they are not observable through the Raman characterization. From the point of view of IR and Raman, in centrosymmetric molecules the Raman active modes are IR inactive and vice versa. So you will have to analyze both if you want to know about all possible vibrational energy levels. In molecules with different elements of symmetry, certain bands may be IR active or inactive, so a variety may occur, but in a complex molecule where you don't find any symmetry, both IR and Raman, you may find them active, but their activity may differ in different cases. So some of the peak is highly IR active, and that is in case of Raman is slightly active, and some other cases may also happen. This complementary nature is due to the electrical characteristic of the vibration. In the first example, where you can see this molecule is highly polarized. So highly polarized molecules, they show very less change in polarization when some energy falls on it or there is some change in length. We can also come to the conclusion that polar bonds are comparatively weak Raman scatterer. That is the reason water is a weak Raman scatterer but a high IR absorber. So in case of infrared spectroscopy, moisture is a problem, but in case of Raman spectroscopy, moisture is not a problem. On the other hand, if we look at the molecule, that carbon-carbon molecule, which is a neutral bond, so when some energy falls on it, it shows a high change in polarizability. So when there is a high change in polarizability, that is the reason that this becomes strong Raman scatterer but weak IR scatterer, because there is no change in its dipole moment. This is the fundamental difference between these two characterization techniques. Sometimes both of these are complementary with each other, but sometimes we need both of them to understand a material completely. But the best part with the Raman characterization is that because moisture is not a problem for this characterization. Adding more to this, in molecules having inversion symmetry, either Raman or IR mode is active because of mutual exclusion principle. One of the common example for this is CO2, carbon dioxide. This molecule has inversion symmetry. So let's look at which modes are Raman or IR active or inactive. In first case, when there is a symmetrical stretch, overall there is no change in net dipole moments. That's why this is IR inactive, and on the other hand this will be Raman active. In the second case, there is an asymmetric stretch. We can see that this will surely cause a change in dipole moment. So this is IR active but Raman inactive. In the next case, 3 and 4, either we can say in plane bending, carbon atom is moving upwards and oxygens are moving downwards, and this can also happen when carbon is going inside the screen and oxygens are coming outside the screen. So both of these are same kind of things but perpendicular to each other, like, or we can say that they are degenerate vibrations. In this case as well, there is change in dipole moments. So this is IR active, and in contrast we can say they are Raman inactive. And in the summary of this part, we have come to the conclusions that IR and Raman can provide the same information by different methodologies. IR is correlated with the change in dipole moment and Raman activity is correlated with the change in polarizability. In clear words, we can say Raman is correlated with the asymmetric change in polarizability, whereas IR is characterized by the change in dipole moment. The IR and Raman data of centrosymmetric molecules complement each other Raman is active, then IR is inactive, and vice versa. And in complex molecules, both IR and Raman show their activity. By now, we have learned a lot about this technique, the science behind, and then what are the normal modes and what is the basic difference between IR and Raman. Now, in this part, we are going to discuss about data interpretation. So, how do we characterize this and how do we interpret its data? The data, the intensity, basically we observe here, we call this as a Raman shift because this is not an absolute wave number. For an example, if you are using a green laser and you are incidenting that light on it, consider 514 nanometer. Then the scattered light may show you 515, 516, 517, 518 nanometers. So at different wave numbers, you may observe different intensities. And the change with respect to the incident light is called as Raman shift, and we measure this in terms of wave number centimeter inverse. So by theoretical calculation, we know some of the results that okay, these results may come, and then we do experimental study and match the result with the theoretical calculation. Or you can check the literature, what are the possible reasons for that peak or what are the names of that peak that you can see in your data. These are two ways through which you can analyze your Raman data. This is the example of barium titanate, which is yttrium doped. This is from my own research paper on Raman characterization. Through literature, I analyzed that, and this dip at 181, this broad peak at 259. So these are because of these reasons which are written in this table. But now let's do some comparative study. If you are adding something to your base material, so what the changes should occur in your Raman data. So I'm broadly mentioning these things, that what should happen in your sample when you change something in that structure. But before that, we should understand the same thing, that the Raman shift corresponds to the energy of the vibrational level. So whenever there is a high change in energy, then your Raman shift will be more. In cases when there is a low change in energy, then the Raman shift will be lower. And in this way, basically we can understand their energy is directly related with the Raman shift. So in this case, we can see that this energy of a particular mode can be modified by changing the value of K and changing the value of M. So either we change the nature of the bond, bond strength, or interatomic distance, or the mass of the atom involved in that chain. In both ways, we can change the energy of that normal mode. So as the energy decreases, mode shift to lower wave number, it is known as red shift. And on the other hand, when its energy increases, this is called as blue shift. But one more thing to understand at this point is that there are too many modes overlapping with each other. So we don't see these modes individually, we basically deal with the envelopes. Envelope is the overall covering we see because of the combination of some modes. So whenever there is a rise in a mode, there is a shift in a mode, or broadening of a mode, these three kind of phenomena may happen. But because of that, we only see the change in the envelope, which may look different than these phenomena. So we can do literature survey for that, and also we can do peak fitting. So in this case, we can see that when this mode is rising, there are three modes in this picture: purple, blue and red color, and in the black color you can see the overall envelope made by the sum of these three modes. Maybe you are adding some functional group, and because of that group, this mode which is related to that functional group is rising. But you can see, as this mode is rising, this broad region on the right hand side is also seems like this is shifting towards left. So sometimes this is not a shift but only a rise in the mode. So a careful observation is required to understand what is happening beneath this envelope. So as we can see in this data from my original paper, the black line is representing barium titanate, And as we are moving towards red and green, in barium titanate I have added tin. A new mode is rising near 197 centimeter inverse. We can also see that the mode near 260, it seems like it has red shifted towards lower wave number, but this is not. There may be a slight variation, but this is majorly looking like this because of the rise of this mode near 197. We are overall dealing with the envelope, not with individual modes. So that is the major thing to understand at this place. Sometimes there is a genuine shift in the mode. So you can see in this case there is a genuine shift in the mode. This may happen if you change the temperature, bond strength changes because of pressure. Maybe the material is compressed and their interatomic distance decreases. In that case, the energy of some mode may change, and here is one of the example. You can see this mode near 305. So as I am adding tin to my barium titanate, this changes the bond strength, and this mode is shifting at lower wave number. Its intensity is also decreasing because this is related to tetragonal structure of barium titanate. As that tetragonal nature decreases, its intensity decreases. Here also we can see a shift in this mode, the mode which is present at 259. Now because of some yttrium doping, it has shifted towards higher wave number, and correspondingly you can see a slight dip near 216 centimeter inverse, which is nothing but just because of shifting the envelope is behaving like this. And there could also happen a broadening of a mode in some cases when there is a particular bond of particular strength, but because of some impurity in the material or we have added some dopants, that bond strength changes. Now that bond is not of a particular strength anymore. Now that bond is of a variety of strengths. In the Raman spectra as well, you will see the broadening of that mode. Similarly, you can go through the literature related to your material and you could find several connected reasons which are causing the same kind of effect. But you can pick the idea that maybe in your material there are more impurities, that's why this is happening. You have added something, or that doping has crossed a certain level, after that this effect is happening. So there could be many explanations to it, but in a broad way I have explained this to you. Also, you can add this to your knowledge. Different functional groups exhibit characteristic Raman bands or say modes at specific wave numbers. So when we talk it modes, so we refer to normal modes, and these are not sharp peaks, they are basically broad peaks. So that's why they are also called as bands. So don't confuse between these two terminologies. For example, carbon oxygen stretch in ketone shows a band around 1700 centimeter inverse. In this way, these are some characteristics mode related to some functional groups present in the molecule. You just take a handheld device and observe the Raman spectra and see its spectra, and you can easily identify that functional group is present or not. Not all functional groups are equally Raman active. Aldehydes can be difficult to detect because of its weak signal. These kind of information related to your material you can gather from the literature. Overall, if you change the chemical environment around any functional group, the position of its band and its intensity may vary. Taking this characterization part to the conclusion, we have summarized in this part that the change in the mass or the spring constant can result in the change in energy, and that can correspondingly seen in Raman spectroscopy through the shifting in the modes. Spring constant K is basically related with bond strength, and any variation in the bond strength or structural change will change in the value of K and the energy related to it. These Raman modes can be altered by the presence of functional group, any structural change, any environmental change may change a Raman mode. But always remember the main thing, that we are dealing with the envelope, not with the individual modes. So what is happening under the blanket, it's far more important to interpret rather than just looking from the top. which you can easily understand just by applying some knowledge of your material and its structure. So Raman spectroscopy along with the information provided by IR spectroscopy can complement each other and can provide the complete understanding of the molecule. So this is the characterization part. So that's it. Thanks for watching about Raman spectroscopy. Once again, this video is sponsored by you. Please don't forget to contribute whatever you feel is okay for this content on the links given in the description. I will see you with more knowledgeful content like this. Till then, bye bye, take care, have a very good day.